אוקיי, נראה לי אנחנו נעבור לאנגלית. Okay, so today we have Assaf Hochman from KIT and Chezi. Can you introduce our speaker for today? Go ahead.
Yeah, it is a pleasure to have Assaf Hochman. Assaf did his undergraduate at the Hebrew University in the Department of Geography. Then he did his master and PhD with Pinchas Alpert at Tel Aviv University. He completed his PhD in 2019, and since then he is in Germany, in KIT, doing his postdoc. Seems to be a very productive postdoc. And today we will talk about reducing the uncertainty in extreme weather and climate prediction. So, Assaf, go ahead.
Thanks a lot. So I will share my presentation. So can you see it now?
Yeah.
Yes, we can.
Okay, perfect. So thanks for having me, and thanks, Chezi, for the introduction. So in this talk, I will give an overview of some of the work and some examples related to dynamics and predictability of extreme weather and climate over the Eastern Mediterranean. I will separate the talk into two parts. Okay, after the first part, I hope to have some clarifying questions or burning questions, and then we continue to the second part. The first part will focus on extreme weather. So as an example, I will give cold spells associated with snow in Jerusalem. So you can see here a picture from my parents' window apartment in Jerusalem, and during the Alexa December 2013 event. This is considered the costliest natural disaster ever recorded in the Eastern Mediterranean. And some of my talk will just give some examples on this single case. And after a few questions, we will go to the second part of my talk, which will focus on climate projections. And I will focus a bit more on dynamics of the Red Sea Trough, and especially of the seasonal cycle in future climate. So I would like to remind you that atmospheric predictability can generally be divided into two parts. One would be the model-dependent predictability, okay, the ability to predict, which we often term practical predictability. And the other would be the model-independent, which we often term the intrinsic predictability. The model-dependent or the practical predictability depends on the accuracy of the initial conditions in the model, the representation of subgrid scale processes, the model ability to simulate the atmosphere, so the governing equations in the model, and the state of the atmosphere. The practical predictability is often quantified in an ensemble model by computing the spread among the different members of the model. So it would be just the standard deviation among the different members, okay, for a specific variable, let's say temperature or sea level pressure or whatever variable we are interested in. The intrinsic predictability, on the other hand, only depends on the state of the atmosphere. And what do I mean by that? So if you think of it, any dynamical system that we want to predict its evolution will, the ability to predict it will depend on two important metrics. One would be how persistent the system is. So a more persistent system would be, we would consider easier to predict its evolution. And the other metric would be how many options does the system have to evolve into or from. So a system with a low number of options, let's say just one, it would be easier to predict its evolution. Just giving an intuitive view of this idea, Let's say we want to predict the location of different people in the university, in the Hebrew university. Okay, we can generally divide the people in the university into a few subgroups. One would be the bachelor students. Okay, bachelor students would be considered not so persistent at sitting at their desk and studying, and would be considered having many options on where to go to in campus. So different courses or many courses to go to. So we can say generally on a bachelor student that it would be more difficult to predict his or her location on campus. On the other hand, a PhD student would be considered more persistent and sitting at his desk and with less number of courses to go to, so less number of options to go to. And then we can say that predicting the location of a PhD student would be much easier than the bachelor student. On the other hand, the professor might be something in between the two. So not as many courses to give and would be considered more persistent perhaps at sitting and teaching, something like that, okay? So recent developments in dynamical system theory allow us to compute these two important metrics for atmospheric state. So for two-dimensional variables in the atmosphere, the persistence and the local dimension. What we do in practice is we view the atmosphere as a long trajectory in phase space, where each point here corresponds to a single two-dimensional map, let's say sea level pressure or geopotential height or something of the sort. Then we compute the Euclidean distance between this single day and all other options in our data set. So in this case, perhaps the NCEP NCAR reanalysis or any other reanalysis data set. Okay, and we can do it for different temporal resolutions, if it's daily or 6 hourly, etc. Once we have these Euclidean distances from the state of interest, okay, we define a small region around our state of interest, a single day. Okay, and with this, within this small hypersphere, we compute d and theta. So d in general would just correspond to the number of options the system can evolve into or from in this small region in phase space. And theta would be how fast does this evolution occur. So is it a persistent system or is it a non-persistent system? Okay. If we give some more intuition on this notion, so let's say we are interested in a specific day and at a specific atmospheric state that we have at that day or a synoptic situation, then a persistent system would be here on the red diagonal, and then theta would be lower, okay? Whereas a non-persistent system would be on the green diagonal, and theta would be higher, or a very non-persistent system or an extremely non-persistent system, theta would be 1, okay? D, on the other hand, gives the number of options the system has to evolve into or from. So you can see that there's here 2 options. So D would be 2. So in practice, what we did is we classified the daily synoptic systems over the Eastern Mediterranean. So Red Sea Trough, Persian Trough, high pressure systems, Cyprus lows, and Sharav lows. I take it for granted that you know what I mean, but if it's not, I can clarify this. And then we have for each day the local dimension and the theta for that specific day. And we wanted to see if D and theta can differentiate well between the different synoptic systems. So we were quite excited to see that actually when you look at cyclonic systems here in red and both, you see that both D and theta are high, so we can consider a low predictability system, as we might expect for cyclonic systems. Okay. On the other hand, when you look at the Persian Trough here in green and Red Sea Trough, we see a more persistent system and with a lower local dimension, so perhaps easier to predict systems on average. Okay. So more details on this aspect you can see in this article, which was published last year. So since we saw that d and theta, dynamical system metrics, can differentiate well or relatively well between the synoptic systems, we wanted to go and to see how well do they do in extreme weather. And this is the first part of the talk. Okay. And not just extreme weather, we focused on cold spells as a first, which cold spells associated with snow in Jerusalem, we can generally say that the large majority of them are associated with cyclones. Okay, so we had a few main objectives for this study. First, we wanted to characterize cold spells from a dynamical system perspective, so d and theta. Then we wanted to characterize cold spells from both a dynamic and thermodynamic point of views. Once we have these two, so these two different fields of research, we wanted to provide evidence for the underlying physical processes that influence the intrinsic predictability, so relating 1 and 2 together. And as a last part, we wanted to also provide insights as to the complementary nature of the dynamical system approach to numerical weather projection, okay, to see if we can use the dynamical system approach in actual weather, extreme weather forecasting. Okay, so what we did is we differentiated our data set into two subgroups. One is the cold spells associated with snow in Jerusalem. This is according to a list we got from the Israeli Met Service of snow events since 1948. And the second group is the Cypress lows according to the semi-objective synoptic classification, which are not associated with snow. Okay, so we call them regular Cypress low, let's call them. Okay, you can, and of course we computed d and theta for the entire data set, so we can compare the two subgroups. Okay, you can already see in the mean composites that cold spells are significantly different from Cypress low. They have deeper and easterly Cypress low and a deeper upper level trough at Z500. Okay. So as I said, we computed also d and theta for these two subgroups, and in order to compare between the two subgroups, we first deseasonalized the values. Okay, because you can, as you can see here, this is the seasonal cycle of d and theta as computed for both sea level pressure and for Z500. Okay. And we want to compare between the groups, so we don't want the seasonal cycle to affect this comparison, okay? Because you can see already that d and theta during summer months are very low, so more stable flow characteristics here at sea level pressure, as we might expect in the Eastern Mediterranean, and higher d in the transition season, so more synoptic systems interacting with each other, so more erratic or a less stable flow characteristics in the transition seasons. And then when we compare the different groups, we first looked at the daily values of these metrics. Okay, so you can see here cold spells in blue and Cypress lows in red, and we compare the different distributions. And at the top you see for sea level pressure, d and theta, and at the bottom Z500 d and theta. Okay, so you can already see that there's a larger local dimension for the cold spells, though this was not significantly different. Whereas a lower theta, so higher persistence for the cold spell events. When you look at the upper levels, you see very high persistence and a lower local dimension. So stable flow characteristics at the upper levels. Okay, the higher persistence for a cold spell, we might say that in order to advect cold air masses into the Eastern Mediterranean and produce a snow event, we should have a more persistent situation. Okay. The next step, after looking at the daily values, we also had the idea to look at not just the daily, but also the temporal evolution. How does the temporal evolution of the dynamical system metrics look for cold spells here on the left and cypress lows here on the right? Okay. As you can see, so 0 here is the onset of the event for cold spells and cypress lows, and you see already that the local dimension, as we saw also for the daily values, is higher than the local dimension in the cypress lows, and you see a peak so lower predictability in the 48 hours before the onset of the event. Okay. On the other hand, at the upper levels, again, we see a very stable flow characteristics at the onset of the event as we compare it to cypress lows on the right. Okay, so the next step was going a bit more into the thermodynamics and dynamics of these events. So we compared again cold spells here in blue and red, and cypress lows in red. And we use the Lagrange framework in order to compute backward trajectories for these two types of events. And you can already see in the dynamics that the trajectories for cold spells show a much more meridionally oriented median trajectory. And the air masses here in shading come from much northerly locations as we compare it to the regular cypress lows. Okay. So again, looking at the thermodynamics, we saw that cold spells show much colder, you see here the potential temperature, much colder air masses already 10 days before the onset of the event. And the interesting thing we wanted to a bit study more was an increase in a large increase or a significant increase in the last 48 hours of both potential temperature, temperature and specific humidity, as you can see here, when you compare it to the cypress lows. So you can see here this feature. Okay. After looking at the climatology, so all cold spells compared to all cypress lows, we wanted to go also into a case study to see if the case study shows similar things to what we see in the climatology or completely different. Okay, so we chose the Alexa event, which I mentioned at the beginning. And you can see already that Alexa was indeed an archetype of an Eastern Mediterranean cold spell. So from the dynamics, you see a deeper upper level trough and an easterly cyclone. And when looking at the dynamical system metrics, we see the same evolution. So this peak before the onset of the event and a minimum at upper levels. So stable flow characteristic at upper levels. And indeed, Alexa was not only an extreme weather event, as I mentioned at the beginning, but it was also a dynamical system extreme. So these values are actually at the upper percentile of the cold spell distribution, of the entire distribution, actually. And also, these values are in the very lower values of the D and theta distribution. Okay. Looking at Alexa from a dynamic and thermodynamic point of view, again, Alexa was an archetype. You see this meridionally oriented backward trajectory, okay, and the air mass is coming from much northerly location already 10 days before the onset of the event, okay. And the same feature we saw for the thermodynamics, this strong increase in potential temperature and specific humidity in the last 48 hours. So our hypothesis was that the passing of the air masses over, the cold air masses over the Eastern Mediterranean or over the warm Mediterranean waters is what, and these air-sea interactions is what influences the changes, the strong changes in these variables, okay? And what we wanted to see if this strong change also influences the intrinsic predictability of this specific state of the atmosphere. So what we did is compute the changes in the last 48 hours for specific humidity, since we're interested in air-sea fluxes, for all of the Cypress laws. And we compared two extreme parts of this distribution, the upper 10 percentile of these change and the lower 10 percentile of these changes. And you can see this in this figure. So we have d and theta, and we have the upper 10 percentile of the changes in specific humidity and lower 10 percentiles. And you see that here in blue, we have a larger local dimension when there's larger air-sea flux interactions, and we have a lower theta at the same time, so higher persistence. And if you compare this, what I showed in the beginning for the daily values of sea level pressure, this shows the same pattern, I would say, okay? Higher D and lower theta. So this does not give causal relationship, but it does give a plausibility argument for the important influence air-sea fluxes have on the intrinsic predictability of cyclones in the Eastern Mediterranean. Okay. Not just that, we wanted to go to see also two other metrics of the cyclone. One is the location of the cyclone, and the other is the depth of the cyclone. So we grouped the different cyclone to deep lows and shallow lows, and we compared d and theta for both sea level pressure and geopotential height. Okay, and you can see here that the deep lows show higher d and higher theta, whereas when we compare eastern versus western lows, we see higher d for the eastern lows and lower theta. Again, this resembles what we showed for the cold spells, which are associated with more easterly lows. Okay, we did the same for geopotential height. And you can see here that for the geopotential height, when comparing deep lows to shallow lows, there's lower D and lower theta, so much stable flow characteristic at upper levels for the deep lows. Again, this corresponds nicely with what we showed for the cold spell events. Finally, we also wanted to provide some evidence or first results as how D and theta can be complementary to numerical weather prediction ensemble forecasts. Okay, so we computed the spread for sea level pressure. Okay, the model spread for sea level pressure, if you remember what I showed in the beginning. And we saw that when comparing cold spells to Cypress law, indeed cold spells show a larger spread and compared to the regular Cypress laws. And the spread, the practical predictability is also lower, so high spread, low practical predictability before the onset of the event. Looking at Alexa, okay, so here in red, you see this peak in the 48 hours before the onset of the event for the model spread. So this corresponds nicely also to what we see from the intrinsic predictability values of D and theta. So to conclude this first part, we show significant differences between cold spells and regular Cypress laws from a dynamical systems perspective. It seems that the cyclone's location, depth, and magnitude of air-sea fluxes play an important role in determining the intrinsic predictability of a cyclone. Extremes in dynamical system metrics also correspond to real-life extreme weather, so we showed this for the cold spells and for the single case study of Alexa. And we hypothesized that this simple and inexpensive calculation, when compared to, for example, numerical weather prediction, running a numerical weather prediction model, may have aided the weather forecasters in estimating the intrinsic predictability, at least for the Alexa storm, okay, with respect to all historical events. The dynamical system, as I said, proved to be complementary. And this is a completely new approach, and we believe that it can be fruitfully applied to other regions and weather extremes, not only in the Eastern Mediterranean. And in fact, we tested this also on heat waves over the Eastern Mediterranean. This paper was just accepted on Friday, last Friday. And a paper in preparation which focuses more on Euro-Atlantic weather regimes. So some more details can be found in this article, published just 2 months ago, I think. And I will be happy to have some first questions on this part of the talk, if you're still there.
Nathan.
Are you still there, or did I talk to myself?
No. You're all here.
Also to yourself.
Yeah.
So I have actually a comment and perhaps a clarification, if you will. How exactly do you calculate those two metrics, dynamical system metrics, the theta and d? What exactly do you do to evaluate it? Take an ensemble and what exactly is involved in the calculation? And the second thing is, you said it's an inexpensive way that complements the Met Office decision-making or forecast producing, but is there a way of quantifying the ease of use against other means that they are using?
So I will just go a bit back perhaps here. No, it doesn't go. So in general, what we do is we view, as I said before, we view the atmosphere as a long... Can you hear me?
Yes.
Yeah, we view the atmosphere as a long trajectory in phase space.
But it's an infinite dimensional space.
Yeah, but what we use is the whole, it's a finite dimensional, because we look now at only the trajectory for example, the NCEP reanalysis database. So we use all days in the reanalysis dataset from 1948 to today, let's say, okay? And of course, we estimate if we had an infinite data set, that would be perfect. But we have to estimate according to the data set we have. So today we actually can do this because we have already 70 years of a data set. Okay, and we believe that it gives good estimates of these two metrics. Okay, so in general, what we do is compute each point in phase space. So this two-dimensional variable is, we compute the distance between that variable to all other daily two-dimensional maps in our data set. So this would be the first part, to estimate the distances and how similar this state is to all other points in our data set.
The similarity includes all meteorologic variables?
So we do this for a two-dimensional variable. So we looked at sea level pressure and geopotential height, but it
so you transform it to a two-dimensional phase space. Okay, now, and the phase space, according to what you think is the relevant variables. Yeah, so here we looked at these variables. Of course, this can be done to any variable, but an important thing or a comment to say is that we see that D and theta are not very sensitive to the resolution of the data set. Okay, when we computed for variables like sea level pressure and geopotential height. So this is an important aspect. If we would compute it, for example, for precipitation, this is a different thing, because the precipitation is influenced very strongly by the resolution in the reanalysis or model. Okay, so then, or wind that suffers high accuracy.
Yeah, or wind, for example. So here we used for these variables, but any variable can be tested.
Okay. And how expensive is it to run?
So this is the nice thing about it. This is a code of 7 lines in MATLAB, so it's not very expensive. You have when you have the whole data set backwards, for example, the ECNWF data set, you can compute it, and it's not expensive as compared, of course, to running a full ensemble.
Yeah. So what is it in computing time? Are we talking about minutes, hours?
I would say minutes to minutes. Yeah, minutes. Minutes to maximum, I would say
That's
an hour, depending on the region you're looking at.
Okay, thank you.
Any other questions?
I think you're good to go.
Yeah, so should I continue?
Yeah.
Everybody happy by now? Okay. So this next part of the talk would be focusing more on climate projections and predictability in this aspect. So I believe that all of you are familiar with this figure, which just shows the global annual average surface temperature change in observations and as projected by the different global circulation models into the future. Okay. The problem with just such a figure is that each point on this graph actually averages first different days on different seasons, so summer days with winter days, and also averages different regions, so Eastern Mediterranean climate with Antarctica climate. Okay, it's much more robust and perhaps even more interesting to pinpoint similar days along this graph and see how they change as we increase greenhouse gas concentrations into the future. Okay, so for example, pinpointing Cypress lows and Red Sea trough systems and seeing how does the increase in greenhouse gas concentration influence the characteristics of these systems. So in the first study, what we did is classify all the days in 8 CMIP5 models, so the global circulation models from the different big institutions. And we looked at how do Cypress lows, the cyclonic events over the Eastern Mediterranean, change for different periods and for different RCP scenarios. So moderate scenario would say an increase by 2040 in greenhouse gas concentrations and then a decrease, or a continuous increase in greenhouse gas concentrations throughout the 21st century. Okay, and you can see that all of these models show a robust decrease in the number of Cypress lows as projected into the future with increase in greenhouse gas concentrations. Okay. The next step was not looking only at the frequencies, but also looking a bit more into the dynamics. Okay, so as one aspect, we looked again into D and theta, okay? And we compared the distribution for the historical period and for a large increase in greenhouse gas concentrations. And what we find, though not very amazing here, but significant, is an increase in both D and theta. So lower predictability as we increase greenhouse gas concentrations into the future. Looking at this from a different point of view, we also computed for the same models the transition probability matrices. So how do the transitions between the systems look, not only for the frequencies, but how do the transitions look? So for, you see here, again, Red Sea trough, Persian trough, high pressure systems, Cypress lows and Sharav lows. And on the diagonal here for the multi-model ensemble mean, you see the persistence of the different systems. So what we found quite robust is that there's a decrease in the persistence of Cypress lows. Okay, you see here the number in percent, and a significant increase in the persistence of the Persian trough, the summertime synoptic system. But for Red Sea trough, we did not see any significant differences. You can see throughout the models, perhaps small increases, but not significant. Okay. Another aspect of this system is their seasonal cycle. This is an important aspect because this can influence different impact in different ways. For example, agriculture, health, etc. And actually, just as an anecdote, we tested how changes in the different systems influence health. For example, here in a study done for influenza, but I will not focus on this aspect in this talk. Okay, but what we found quite robust for all models here for an increase for the RCP 8.5 scenario, you see an increase in the length of summer time. So this is as defined according to the Persian trough system, and a significant decrease in the length of winter time here in blue as defined according to the Cypress law system. Okay. But again, for Red Sea troughs, we did not, or for the Sharav law, we did not find any significant changes in this figure. And this is just showing it for the Red Sea trough. As we, for the RCP 8.5 scenario, you see not very large changes. We see perhaps small increases in the wet season. Okay, here and here. So earlier studies, like Alpert et al. In 2004, found in reanalysis, in NCEP reanalysis, a very strong increase in the number of Red Sea troughs. On the other hand, Saaroni et al. Just recently, using an automatic identification of the Red Sea trough over the Eastern Mediterranean, did not find any changes in the ECMWF reanalysis, okay, throughout the historical period. Peleg et al., on the other hand, in 2015, found an increase in the active Red Sea trough as projected into the future. Okay. But a peculiar aspect of the Red Sea trough, as you may all know, is that it can generally be divided into two subgroups. One would be a wet Red Sea trough associated with precipitation, and a dry Red Sea trough, usually associated with easterly windstorms, dust, etc. Okay. So what we wanted to see, if looking into the global climate models and differentiating between wet Red Sea troughs and dry Red Sea troughs, is there now a significant change in either of these systems, or as we showed earlier, no changes at all? Okay. So in order to define the wet Red Sea trough compared to the dry Red Sea trough, we use the statistical downscaling algorithm based on past analogs, you can see here. And we downscaled the different days into the to 18 stations over the main groundwater basins over Israel. Okay, so we did not look here at southerly locations at the Negev or Dead Sea, but all over the main hydrological basins. Okay, and then the Red Sea trough was classified according to the semi-objective synoptic classification, and we have the daily values for precipitation for the present and for the future in the GCMs. Okay. The threshold defining a wet Red Sea trough is defined here as rainfall at least for 2 stations above or equal 0.1 millimeter, which is a common definition already suggested before. Okay, and now we looked at the same aspects, but comparing the different groups. So here for wet Red Sea trough, we see the seasonality. And now we see a significant decrease, you see, in the number of wet Red Sea trough. especially in the transition seasons. Okay, this is for the multi-model ensemble mean, when you compare the black line to the red line in the future. Looking at the dry Red Sea trough, on the other hand, again, you see that there's a significant, now you see a significant increase in the dry Red Sea trough as we look into the future, but now it's mostly situated in the wet season, so transition seasons and winter. But these are two very important aspects, because now we see that if you think of it, Cypress laws, we show that there's a decrease in the frequency and decrease in the amount of precipitation. And if we thought that perhaps the wet Red Sea trough would compensate for the decrease in precipitation in Cypress laws, this is actually not the case. We see that there's a decrease in the wet Red Sea trough, but an increase in the dry system. And we see also for the precipitation, the daily precipitation values here computed for the average of all the stations, we see that the models are quite robust in predicting a decrease in precipitation also for the daily values of the wet Red Sea trough. Okay, so to conclude this second part and the whole presentation, we find a significant decrease in the occurrence of the wet Red Sea trough and a significant increase in the frequency of the dry Red Sea trough. The decline in the frequency of the wet Red Sea trough occurs primarily in the transition seasons, while the increase for dry Red Sea trough is found throughout the wet season. And we show that the daily rainfall associated with the wet system is projected to significantly decline by the end of the 21st century. And these findings are in line with a poleward shift of the mid-latitude jet stream on zonal and annual average, which is also associated with a northward shift of mid-latitude storm tracks. And in fact, we believe that these changes may allow the Red Sea trough to penetrate further north and in turn influence its rainfall yield. Okay, some more details can be found in this study. And I will leave you with this cartoon, which I think summarizes well what I talked about. So we talked about weather extremes predictability. We perhaps did not talk about the worst New York City blizzard, but the worst Jerusalem blizzard, if we can call it that way. And on the other hand, we looked at climate projections over the Eastern Mediterranean, and we focused on the synoptic systems and their characteristics for the future. So with that, I thank you and will be happy to hear questions on this part and on the whole presentation. Thank you very much.
Thank you, Assaf. It was an awesome talk. Chezi, do you want to handle the questions?
Yes, although I can hardly see the participant, but maybe I will start. So I have two questions. I actually tried to ask before, but for some reason you didn't hear me. Did you try to work also with a phase space larger than 2 variables?
What do you mean?
Instead of just say sea level pressure and geopotential, maybe to add another variable. And
so we looked also at temperature, but as I said, we focused on these 2 variables. But what we did test is how we can compute the different variables together. So for example, sea level pressure and geopotential height together, their interaction. But I must say for this study, we did not find that it was very helpful to use 2 variables together. But we did not look at many other variables, just at sea level pressure, geopotential height, and temperature.
Okay, now before I let other people to ask another question, did you try to estimate effect on global precipitation by the decline of Red Sea trough and the decline of Cyprus law. Try to estimate what will be the total effect on precipitation.
So we did compute it separately, but we did not compute them both together. But we do have values, I think, for the total precipitation over Israel. And if I remember correctly, the decrease is about 15%, if I remember correctly the number, but I don't want to say a number without checking.
Okay. Anyone else? I think just interrupt because until you will quit the screen sharing, I cannot see who is trying to ask.
Okay, should I quit it just perhaps, and we can talk?
Okay, try, and then maybe if you need another figure, you can join.
Okay.
Okay. So anyone want to ask?
Well, for the Red Sea trough, wet and dry, the main difference is not in the surface configuration, but in the upper level configuration. And that is, so I personally don't believe that it would make much difference for the conclusions, but why don't you take the more robust signal for the wet and dry?
So I just showed the surface values, but we actually classify the systems according also to the upper level, of course. And in terms of precipitation, we of course used also the upper levels. I just showed the difference in sea level pressure because the figures with upper level are a bit more messy, but it is computed with the upper level, and the precipitation it's just the same. Yeah.
Okay, toda.
I hope this answers your question. Yeah, of course, the upper level is very important for the Red Sea trough.
I have a question.
Yes, please.
During the last decade, papers by Alpert group showed that there is a tremendous increase in number of Red Sea troughs. Now you say there is actually is no different. Does it mean a change of the how do you define the Red Sea trough?
So actually what I say is not that there's no change, but there is a change, but there's a difference between changes in wet Red Sea trough and dry Red Sea trough. Like Alpert et al., which of course was my PhD supervisor, in 2004, he showed for ENSEP reanalysis, looking at all the Red Sea troughs and seeing an increase in the number of the systems, but they did not differentiate between wet and dry, okay? And actually what they say in that paper is that they believe that global warming or the changes show an increase in the dry Red Sea trough. So actually what I show in the GCMs follows what Alpert et al. 2004 shows, but not the other papers, I would say. So I hope this explains. So there's an increase in the Red Sea trough, but it's important for this system to differentiate between the two groups, because if you look at all Red Sea trough, you just combine the active systems with the non-active systems, and it's, I would say, less robust. Did that answer your question?
Anyone else want to ask? Okay, so let's thank Assaf. I think it was a great talk.
Thank you so much.
Yeah, we'll be in touch. Bye-bye.
Bye-bye. Thank you so much for having me.
תודה, אסף. תודה, אסף.